Okay, there's the blood vessel and your two multiple choice. And then we just gotta find the second page where we do all of the plus C ones. So that looks like it. There it is. Okay. So that is that first part. So the blood vessel problem, that was an AP exam. That's why I wanted to show, actually show you this part of it. So all three of those first questions were from AP exams. And that part that you had would have been part A and part B. And it would have been 4 of the 9 points. So if you got part A and part B for that word problem, you could have obtained 4 of the 9 points on that question. So what they were looking for is the average value, so that's 1 over B minus A, from 0 to A, and then all you had to do was give them the integrand, which is B of x over 2 and dx. And then down in part B, you can definitely see that that's a Riemann sum. Yep. I don't know why my board does that. And then number 2 was A, and number 3 was C. So if you go back up to that original, the reason that, so one of the questions I usually get asked is why is B of x over 2 and not just B of x? Anybody know why I have it over 2 and it's not just B of x? Give you a big hint. What does B of x represent? It represents the diameter, exactly. And this asks for average radius. Radius is half the diameter. So the reason that it's over 2 is because it's asking for average radius, not diameter. Okay, so that sums up that front page. Like I said, that was all AP. Then the second page are my worksheets. So here are my answers to those. So those were kind of problems I constructed. So the average value of the quadratic from 0 to 2 gives you 1 over B minus A from 0 to 2. So your final answer was 4/3. And then number 6. So that was your average value, but then you were trying to find the point of the average value. So your average value was -6 because your number is not matched. Oh, yours is the 4 to 9. Sorry, I changed my assignments. You're on the other side, maybe. Yeah. You have the one with the quadrants and the calculator. Yeah. Sorry. You're the page that's missing off my handout. So your back, though, this isn't my back. Kind of. I'll find my answer key and give it to you. Or I can do it. Chase, I knew you asked me for two of them. Which two did you ask for? I'll just do the two you asked me for. G and H. I have the page because I have it on the computer open. I still don't know what I did with my answer key. I don't know, you just mumbled. Okay. Oh, you're going to be mad when you see how easy G is. Okay, so letter G, you have the integral from 1 to 8 of the square root of 2 over x. So I would think of that more like 1 to 8. The square root of 2 can come out in front because it's like a constant. So then that gives me 1 over x to the 1/2. Because again, any square root you can take as one big square root. And you can rewrite it as 2 little square roots. So it's like the square root of 2 over the square root of x. So that would become the square root of 2 out in front as my constant over the square root of x here. So then I could think of that as the square root of 2, the integral from 1 to 8 of x to the negative 1/2 dx. And then my square root of 2 tags along. X to the negative 1/2. Well, the rule for integration is you add 1 and divide by that new exponent. So that becomes x to the 1/2 over 1/2, evaluating from 8 to 1. Yep. And then that becomes 2 square roots of 2x to the 1/2, or the square root of x. And you could actually think of that as all one unit, because the square root times the square root multiplies inside. And if I evaluate that from 8 to 1, the reason I brought it in on purpose is because think about 2 times 8 will give you 16. So you get 2 square roots of 16 minus 2 square roots of 2. Square root of 16 is 4. 4 times 2 is 8. So I get 8 minus 2 square roots of 2. Did you say H is the other one? So for the next one, you have to think about the fact that the derivative of cotangent is cosecant squared. So the derivative of this problem is working backwards now. So instead of thinking in terms of derivatives, you think, okay, antiderivative. So the antiderivative of cosecant squared is cotangent. The antiderivative of 2 becomes 2x. So this is 2x. And then think about your derivatives and antiderivatives again. So the derivative of cotangent is negative cosecant squared. So since there's already a negative on my cosecant squared, when I antiderive that, I'm going to get a positive cotangent. So that's going to be positive cotangent x from 5/4, pi halves to 5/4, sorry. And then you plug in. So you get 2 pi halves plus the cotangent of pi halves minus 2 times 5/4 minus the cotangent of 5/4, because that negative here for the f of b minus f of a would distribute to both parts of that problem. And then at that point, you're just going to clean it up. So if you think about cotangent of pi halves, cotangent is really cosine over sine. So the cosine of pi halves is at 90 degrees. So the cosine of 90 is 0. So the cotangent of pi halves is 0. So 2 pi over 2 gives you pi. 2 pi halves. So you're subtracting from pi a half a pi. And then the cotangent of 5/4. Well, the tangent of 5/4 is 1. Cotangent of 5/4 is also 1. So that's minus 1. So you get pi halves minus 1. Anybody else have pi yesterday? What's pi day? Are there any other questions on the handout? Sorry, I don't know. Took my answer key out of my binder, and now I don't have the answer key. Okay. How about from the front? So I got asked for like this, like number 3, multiple choice. So how about did everybody get the multiple choice? You know, we got number 3 for the multiple choice. Because that one was actually from your quiz the other day. And I re-put it on our homework to see if we could get it there. So how many of us actually got C from the homework for today? From the front. Okay, so let's talk about number 3 from the front. That is an absolute value equation. An absolute value equation is a V-shaped graph. 4 minus the absolute value of x. So that tells you that the graph is reflected, and the 4 tells you it's shifted up 1. So my graph is reflected and up 1. So my V is up 4 and open down. What shape does the absolute value graph make? What? Yeah, it's a triangle. A triangle of base, length, and height. So area of the triangle is 1/2 base times height which is letter C. How many of us tried to make that really difficult? Yeah, thanks for being honest. Like, the whole point sometimes of these repetitive types of questions, I wanted you to go back and remember, What was the very first way I taught you how to integrate? Geometry. The very first way we learned how to integrate was geometry. So don't forget to use that as a technique for a question like this. We haven't been taught how to. You mean the math lab? Mm-mm. If I take something to the teacher's lounge, I go teacher's lounge to computer. So like when I make my packets, I make PDFs on the teacher's lounge copier. And then they email to me. Like, you know, when we get like our Xerox emails? Yeah, I send myself them. So I got tired of taking photos and office lines of 17-page packets. Okay. The average value of a cosine or the average value of the curve y equals 3x minus x squared. Okay. Okay, so this one, and this is again, where AP is kind of testing your ability to put into place what you need to know. It says, in the first quadrant. So to get in the first quadrant, you have to find your x-intercept and your y-intercept. Oh, multiple choice. Okay. Well, for the number 2 non-multiple choice, if you didn't know how to find the interval, you had to find your x and y-intercepts so that you could find where the curve hit this axis and where the curve hit that axis, so that you could find the area under the curve from point A to point B, in case we were missing that one too. Okay, so the average value of the cosine, so that's 1 over b minus a, integral of a to b of cosine x dx. So minus a minus becomes a positive, so you got 1 over 8. And then because the antiderivative of cosine is sine, that was sine x from 5 to negative 3. So that gave you sine of 5 minus sine of negative 3 all over 8. And then because sine is an odd function, you could take out your sine function. So a negative sign would actually turn into, which is cruel of them, a negative. Because negative and negative is the same thing. Okay? So, sine, let me see if I can show you. It's that sine's like an odd function. So like if you, what? Like, I'm trying to pull up just a graph of sine so you can kind of see it. There you go. So like if you look at like the sine of x in general, if the sine of negative x, in this case negative 3, it's always equal to the negative sine of 3. So like because of that functionality, they took that negative sign and changed it to that negative sign. Yes, just because it's only because sine's an odd function. Because of like your curve of sine. I don't know how to explain it. It's not going away. It's just that like everything on sine happens at its opposite sign. All right, if you haven't done so, there is a new packet for you back here for you to pick up. I kind of changed what we're doing today, and I'm really happy about it because there are a lot of kids out. So originally I wanted you to do that we were going to do rate in and rate out, but rate in and maybe not a lot of kids, there's just like 2 of you. It just feels like a lot because of the way the room's set up. But I want to do rate in and rate out after we do part 2, which is really part 1 of the fundamental theorem. So what I want to do is actually learn part 1 today, and then tomorrow do rate in and rate out with both, having understood and learned both parts. So there's a packet back here, go ahead and grab that if you have not already done so. All right, so take a minute, and we're going to look at that front part of that handout. So in the front part of the handout, that is a review of where we've been. So that is the fundamental theorem of calc part 1, which is kind of like part 2, in which we were taking into account how to find f of b minus f of a in terms of an average value. So just take a minute, read through that. That should hopefully be a review of what we did last week. And then we'll talk about it in terms of your answers. So again, today we're going to talk about the second part, which is up top. So this is what we're talking about today. This is what we previously talked about. And then the reason I wanted to look at this is because this helps introduce where we're going to tomorrow. So it says if h of t is the rate of change. So remember, rate of change is a fancy word for derivative. So this kind of saying this represents the derivative of the height of a conical pile of sand in feet per hour. What does 0 to 5 of h of t represent? So that represents the integral of the rate of change. So if you're going from feet per hour and you integrate that, then your answer is now going to be in terms of what? Feet. So that integral in that first part would represent the change in height of the cone. So this would represent the change in height. Which would be in feet. And how long would we be looking at the change for? In 2 hours? In 10 hours? In the first 5 hours, because it starts at 0 and goes to 5. So even though my answer is in feet, the answer comes from the first 5 hours. If velocity of a particle moving along the x-axis is measured in feet per second. So we're given velocity. We all know that the antiderivative of velocity is position. Thank you. So this would represent, or that integral would represent, the position of the particle but this time it's not the first 5 hours because we started at 3 and end at 10. And my time is also not in hours, it is in seconds. So it's really a lot of paying attention to your units. So it's the position of the particle in feet from t equals 3 to t equals 10. So you have to make sure that you're really particular about when this is occurring. If there were no bounds, then you wouldn't have to care about the time at which it was occurring. Okay, if B of t is the rate of growth of the number of bacteria in a dish, measured in the number of bacteria per hour, what does that represent? So once again, what would it represent? It would represent the change in bacteria from hours 2 to 6. It's really important to determine what an integral is representing. Can you break down what we're asking you to break down? Do you understand its representation? Are we okay with understanding representations of integrals? So I need to do 4 and 5 on the back. Is it Monday and you're all still asleep? So then what I want to do is move over. They're okay. You feel like you have the understanding of that fundamental theorem down. Go ahead and move over to our notepad. And I'm going to move over to my PowerPoint. Okay. So as part of the warm-up, it says let the function f of x equals x cubed plus cosine x. So what is the indefinite integral for f of x? What would the integral as derivative become? So what we want to do is look at, okay, let's find the antiderivative of x cubed plus cosine x. So, antiderivative of that becomes So that's the case where you get sine x plus c because it's indefinite. So that makes this a family of functions. And now it says what is the derivative of this integral. So if you take the derivative of that, that's like saying d dx of 1/4 x to the 4th plus sine x plus c. So we know that the derivative of 1/4 x to the 4th is 4 times the 4th, which is 1, x cubed. Derivative of sine x is cosine x. And the derivative of any constant is always 0. So what happens when we took the indefinite integral and then take the derivative of the indefinite integral? What do I end up with? I end up with what I started with. So the indefinite integral and derivative of the indefinite integral gets me the original. So that makes derivatives and integration inverse operations of each other. Derivatives and integration are inverse operations of each other. That is what the fundamental theorem of calc, part 1, says. Fundamental theorem of calc, part 1, says, in the lamest of terms, at its most basic wording, that the derivative of the integral is the original. The derivative of the original is the original. So let f be the function continuous on the interval a, b. Capital F of x represents the original function. You're going to antiderive f of t. Then you're going to take its derivative. And we get f of x back at us again. So that's what we talked about on Thursday or Friday last week. This is part 1 and part 2 of the fundamental theorem of calc. On Friday, we focused fully on part 2. Today, we're going to focus on part 1. Tomorrow, we're going to look at rates in and rates out involving both parts. So part 1 broke it down, said that the theorem made this astonishing connection between differentiation and integration. If f is continuous on the interval ab, then the function capital F of x equals the integral from a to x of f of t dt has a derivative at every point x in ab, and capital F prime of x equals df dx, which equals the derivative of the integral with respect to x of f of t dt, giving you f of a. Why does f of little a cancel out when we take our derivative? Why wouldn't this be f of x minus f of a? What's the difference between f of x and f of a? Even go back just to algebra days. If I ask you to find if g of x was equal to x cubed, and I asked you to find g of 3, what am I going to get as an answer? Bethany? A constant. I don't care what that number is. But if I ask you to find g of x squared, what am I going to get? Do I get a number? No. I get a function. The derivative of a constant is 0. The derivative of a function is a function with a power 1 less. So that's why here it's only f of x. I'm very glad that I want to prove this with you because I feel like we're still not totally clicking with what I'm trying to say. So we are actually going to prove the fundamental theorem of calculus. So let's start with the beginning of it. The beginning says that capital F of x is equal to the integral from a to x of lowercase f of t dt. Back when we first started our study of calculus, we learned the definition of the derivative. And the definition of the derivative was that f prime of x is equal to the limit as h approaches 0 of capital F of x plus h minus f of x all over h. That was the definition of the derivative way back in chapter 3.1. So, if I told you to find the derivative of the integral using the limit or the definition of the derivative, that would be like saying the limit as h approaches 0, the lower bound is a, the upper bound in this case is x plus h, because you're finding capital F of x, minus and again, all of these are over h, because that's part of our limit property. Now, you can think of that as one separate limit, or what do we know about integrals and limits? Well, we know that we can write them as wholes. So this is kind of like saying 1 over h, because that's a constant. Limit as h approaches 0. The integral from a to x plus h of f of t dt minus the integral of a to x of f of t dt. So you can factor out that 1 over h constant, bring it out in front, bring your limit with you. Now, what do we know about the bounds of our limits and where they are? Can I have a limit going from x plus h to a? No. Yes, no. You have to match your bounds. So I need x plus h to be down and a to be up. So if I need to flip my bounds, I need to make it a negative. I could also do what with my terms? What if I rearrange the order of my terms? Or what if I flipped these bounds and rearranged the order of my terms? You have very amounts of options. If I multiply this by a negative, I now have 1 over h, limit as h approaches 0. I took the negative of that, so that made it x to a. So now my upper and lower match, which means I can really write this as one integral from x to x plus h. I'm going back up top just so I have space. So that's 1 over h, limit is h approaches 0. The integral now from x to x plus h of f of t dt. What does that 1 over h kind of remind you of? From the other day? What does that represent? See how it's b minus a? X plus h minus x gives you h. So that makes this kind of look like a average value. And when we talked about the average value, what theorem did we relate that to? Someone said it. MVT. So that creates the following statement. Hence, the fundamental theorem of calc. Calculus is about the understanding of how algebraic functions work. It's about understanding why something does what it does and how it does what it does. I also don't expect you to understand it the first time. Sometimes you have to go back and look at everything we wrote and reread it. That's why we do practice. That's why we go through the notes and the theorems and the purposes of them. So on the next page, why? Why do we do this? What does it mean? What did everything I just do tell you? Well, it tells you 3 key pieces of information. Differentiation and integration are inverses. Differentiation and integration are inverses. Continuous functions will always have an antiderivative. And that's something I wanted to talk about. That statement that every continuous function has an antiderivative doesn't mean that discontinuous functions don't. We've misinterpreted that statement. My saying every continuous function has an antiderivative does not mean that a discontinuous function does not. Those are not universally stated. Because some of us were trying to say, oh, it's not continuous, therefore no antiderivative. And that's not the case. That is not the case. Piecewise functions have antiderivatives. So we're now going to take our old fundamental theorem and put a new take on it, which is the derivative of the integral is equal to f of x. And notice how this function goes from f of t, and this goes to f of x. Over here, it goes from the derivative of a to u. So u represents a function, so it's f of u times u prime. So if u is something other than x, so if we take the derivative of the integral to x squared, then you have to apply f of u times u prime. If it's x, it's always f of x. If it's something other than x, you have to apply this part. So let's start basic. Find the derivative of y with respect to x for the following integral. So dy dx is equal to ddx of the integral from 2 to x of 3t plus cosine t squared dt becomes 3x plus cosine x squared the derivative of that integral is 3x plus cosine x squared. Okay. Next example. If anything, it's over on that windowsill. Okay. Find the derivative when y equals the integral from 2 to x squared of cosine t dt. So once again, dy dx is equal to ddx of 2 to x squared of cosine t dt. That's what that's saying. So that equals cosine x squared. However, that upper bound is not x. So according to the rule, you have to multiply by its derivative, which is 2x. So this answer is 2x cosine x squared. And if you did it the long way, think about what that is asking you. It's saying y equals the integral from 2 to x squared of cosine t dt. So that's like saying, okay, what's the antiderivative of cosine? That's sine from x squared to 2. So that gives you sine x squared minus the sine of 2. And then if I said, okay, now take the derivative of that, because this is like y equals, so the derivative of that is a chain rule, right? So the derivative of sine is cosine x squared, and the rule for the chain rule says times the derivative of the inside. Sine of 2 is a constant, so it zeroes out. So we can see long way, new way, same answer. What happens if the x is on the bottom? What happens if the x is on the bottom? Well, our rule doesn't work for that. You gotta flip your bounds. So you gotta get the x on top. So you make it y equals negative the integral from 5 to x of 3t sine t dt. So its derivative is negative 3x sine x. I don't know why I didn't write on your end. It's like frozen. Oh, good. School just lost the internet. Internet on any device. Good. One's connected to an Ethernet cable. Okay. Let's try screen mirroring on the Apple TV. Nope. It's not my fault. It's weird. Okay. In this last example here, let's just create a clean whiteboard. I'll just write on this. So we have y equals the integral from 2x to x squared of 1 over 2 plus e of t dt. You cannot do this as one integral where you have a constant in the top and a constant in the bottom. You have to change for the fundamental theorem so that this becomes two integrals where your denominator is a constant. So you could go 0 to x squared of 1 over 2 plus e of t dt, heads up. And then you can subtract from that the integral from 0 to 2x. So you move this bound up. A constant of 0 does not change anything about your values. So then you make that from 1 to 2 plus e of t dt. If you added it back, you'd see that constant to constant match. And then you go from 2x to x squared. It didn't have to be 0 as my upper and lower bounds either. I could have made this number 8. As long as the numbers on the lower bounds matched, it didn't matter. I could have made it 18 because the derivative of a constant is 0. So it doesn't matter what number you pick to be your lower bound, 0, 8, 18, 100. It's always going to 0 out. So your dy dx is equal to 1 over 2 plus e to the x squared times, because your upper bound is not a linear, you have to multiply by its derivative, 2x, minus 1 over 2 plus e to the 2x times that derivative, which is 2. So cleaning that up, you have 2x over 2 plus e to the x squared minus 2 over 2 plus e to the 2x. Okay? And then your next example, so it says construct a function of the form y equals a to the x of f of t dt plus c. So this is bringing both theorems together. So this is bringing both theorems together. So our function becomes y equals a to x. My dy dx is equal. So we're given dy dx is equal to e to the x tan x. And you want to get it back to that function that we have. And we are told that when y equals 0, x equals 8. So when y equals 0, x equals 8. So what we're doing is integrating this to get it into that form. So we're given the derivative, and we need to integrate it. So this dx has to move over there, so it's the integral of dy equals the integral of e to the x tan x dx. And we're given the initial conditions that when y is 0, x is 8. So how can we make that connection? We know this. We also know this. So make that connection between the two. Well, if this is y, that's like saying this is 0. X is saying it is 8. And if we write this in terms of t's, this is e of t tan t dt. So here's your connection to part 1 and part 2. If I told you to take the derivative of that, it would zero out, hence 0 equaling 0. So if I need an integral to equal 0, what does that a value need to equal? You need an integral to equal 0. What does the a value need to equal? Yeah. So if I need a to equal 8, that makes my function 8 to x of et tan t dt. That's your answer. Now you can take your break. So be back at 45, or 44 rather.